Yeah, good evening, everyone. My name is Haebom Lee, and I'm delighted to be here today to discuss our custom synthetic data for data-centric AI. Let me shortly introduce myself before we begin. I serve as the principal research engineer leading the DAS R&D team at AIMMO. Before joining AIMMO, I worked at several research centers, including Bosch Corporate Research, KIST Europe, the German Research Center for Artificial Intelligence, and MMCI at Max Planck Institute. I'm also pursuing a PhD at Heidelberg University, mentored by Professor Carsten Rother, and possess a master's and bachelor's degree in computer science from KAIST. My core areas of expertise encompass outdoor lighting estimation, simulation, synthetic data generation, and computer vision, which are fundamental to my work at AIMMO and form the core of today's discussion. We will begin by discussing the background and importance of data in AI, understanding why data is often referred to as the fuel for AI systems. Next, we will explore the role of generative models in data-centric AI and how they can be used to create synthetic data that can improve the performance of AI models. Afterwards, we will discuss the need for synthetic data in autonomous driving and how we can help in developing more robust and reliable AI systems. Following that, we will look at how synthetic data can be generated for different operational design domains and the benefits of this approach. Then, we will delve into the case study where we introduce some of our synthetic data projects. We will also cover the concept of data curation in the latent space and how we can help in improving the quality of the dataset. Towards the end, we will discuss the challenges and limitations of using generative models for synthetic data generation. Let's begin by understanding the importance of data in AI, and specifically in autonomous driving. Data is often referred to as a fuel for AI systems. A car needs fuel to run, and similarly, AI systems need data to operate and learn. The more high-quality data we have, the better our AI systems can perform. In the context of autonomous driving, the need for data becomes even more critical. Autonomous vehicles require a huge amount of data for various tasks, such as path planning, interaction with the sensory system, and perceiving the surrounding environment. This data is what allows these vehicles to navigate safely and efficiently on our roads. However, it's not just about the quantity of data. The quality of data is equally, if not more, important. Traditionally, the focus in AI research has often been on refining and enhancing the structure of neural networks to boost performance. However, there's a shift happening towards a more data-centric approach. Data-centric AI is an approach that emphasizes improving data quality, not just model architecture. This is particularly relevant in autonomous driving, where high-quality data is essential for training reliable and safe driving systems. But the benefits of data-centric AI don't stop there. Not only can it reduce training time and the storage needed for data, but it also enables us to develop consistent methods for collecting and labeling images and facilitates the optimization and updating of models. So instead of just building a better engine, we are ensuring that we have the best quality fuel for AI models. As we delve deeper into the world of autonomous driving, we quickly realized that it's a field that requires a multitude of AI systems, each demanding vast amount of data for effective operation. This is where the concept of data-centric AI comes into play. Data-centric AI allows us to use our data more efficiently, as we discussed earlier. It also helps in reducing errors and improving the performance of our AI models, which is crucial for the safety and reliability. One of the key challenges in this field is achieving high-quality data sets and covering edge cases. And this is where the use of generative models becomes highly relevant, seeing that they offer a practical solution to these challenges. And as we move forward, we'll see how influential they are in synthetic data generation. Let's now turn our attention to generative models, a type of AI that can generate new data instances. These models can interpret and manipulate pre-existing data, creating new instances that can be used for training. One of the most well-known examples of generative models is generative adversarial networks, or GANs. GANs consist of two networks, a generator and a discriminator. The generator's job is to create new data instances, while the discriminator evaluates them for authenticity. These two networks compete against each other, and in doing so, they improve the quality of the generated data. Furthermore, another example of a generative model is the diffusion model. A popular type of diffusion model is the stable diffusion, which can generate data based on a given input. For instance, it can generate an image from a text prompt. This provides a powerful tool for synthetic data generation, as it allows us to create specific types of data on demand. In the realm of data-centric AI, these generative models play a pivotal role. They can capture complex data distributions and generating synthetic samples, which are invaluable in enhancing the effectiveness of AI systems. One of the key advantages of using generative models in data-centric AI is their ability to enrich our data sets. They can generate synthetic data that improves the quality, quantity, and variety of data. This not only optimizes the training process, but also allows us to create specific data that might be difficult to obtain from the real world, thereby broadening the scope of scenarios our AI systems can handle. Let's shift our focus to an intriguing research paper entitled "Augmented Reality Meets Computer Vision." This research provides a compelling example of the impact synthetic data can have on deep learning. The authors of the paper propose an innovative approach that combines real and synthetic data to train semantic instance segmentation and object detection models. They augment real-world imagery with virtual objects of the target category, creating composite images that retain the realistic background appearance while introducing a variety of complex object arrangements. The figure on the left side illustrates the significant improvement in the performance of deep learning models when synthetic data is used in conjunction with real-world data. This underscores the potential of synthetic data to enhance the effectiveness of deep learning models, particularly in complex and dynamic fields like autonomous driving. This is another paper that I would like to introduce. It's titled "Fallen Person Detection for Autonomous Driving." As you might imagine, it's quite challenging to find images of people lying on the road in typical autonomous driving datasets. This rarity often results in bad performance when it comes to detecting individuals in such unusual positions, as demonstrated in the image on the left. The authors of this paper tackled this issue by superimposing images of people lying down onto clean road images. This simple strategy serves as an excellent example of how synthetic data can be used to cover edge cases, ultimately leading to an improvement in the performance of the detection algorithm. Let's explore AIMMO's strategy for custom synthetic data generation. At AIMMO, we not only understand the pivotal role synthetic data plays in advancing AI, but also we acknowledge that each AI application is distinct, requiring personalized data solutions. This is particularly vital when acquiring real-world data is both challenging and costly. Our strategy leverages the capabilities of generative models to produce custom synthetic data, carefully tailored to meet the specific needs and requirements of our clients. This bespoke approach to data generation is crucial in enhancing the performance and robustness of AI models and offers several noteworthy advantages. First, it augments the diversity of our datasets, adapting to the unique needs of various applications and thereby improving the model's generalization capabilities. Second, it reduces labeling costs. With custom synthetic data, we effortlessly generate ground truth labels, eliminating the need for extensive manual labeling. Last, our strategy enables us to simulate and address edge case scenarios that are typically underrepresented in real-world data, but are essential for ensuring the safety and reliability of AI systems. Having discussed AIMMO's approach to custom synthetic data generation, let's now shift our focus to an important concept in the field of autonomous driving: operational design domains, or ODDs. ODDs are specific conditions under which a driving automation system is designed to function. These conditions can include environmental factors, geographical locations, and even time of day restrictions. Understanding these domains is fundamental to the safety of connected autonomous vehicles. Now, you might wonder why we are discussing ODDs in a talk about synthetic data. The connection is quite significant. Each ODD has its unique characteristics, and to ensure the robustness and reliability of AI systems, we need to train them with data that covers a wide range of ODDs. This is where AIMMO's approach to synthetic data generation comes into play. At AIMMO, we leverage synthetic data technology to diversify our datasets, simulating a variety of ODDs. This includes not just the common scenarios, but also the edge cases that are often ODD-specific. For instance, we can generate synthetic data that simulates different seasonal or weather effects, or even emergency situations. By doing so, we are not just enhancing the robustness of our AI models, but also reducing the need for extensive real-world data collection on the various ODDs. As you can imagine, collecting real-world data for every possible ODD can be time-consuming and costly. Let's now examine a case study highlighting the impact of custom synthetic data in road defect generation. We are considering the task of detecting road defects, such as cracks or potholes, which is essential not only for autonomous driving, but also for the development of smart city applications. Traditionally, labeling these defects in real-world images has been a labor-intensive process. Guaranteeing the consistency of the labels is challenging due to the diverse appearance of these defects. Now, think of a scenario where we manually create these defects on clean road surfaces. In this manual approach, we simply draw the defect mask for each road defect we aim to generate. This method presents several advantages. First, while it involves manual creation of defect masks, it eliminates the extensive need for manual annotation of real-world images, as the ground truth labels are just automatically generated once the defect is designed. Second, it results in clean, precise, and consistent ground truth, ensuring the high quality of the training data. Moreover, this manual method allows us to generate as much data as needed, making us to cover a wide array of defect types and scenarios. And importantly, this approach cuts down the cost associated with the data collection, as there is no longer a need to physically acquire images of various road defects. Now, you can see that this approach is already beneficial, but isn't there room for further improvement? Let's explore how we can refine this project further with an automatic approach, eliminating the need for manual defect design and offering additional benefits. This method is streamlined, allowing us to generate a road image with specified defects from a clean road image using defect prompts. The automatic process operates in two steps. First, using defect prompts, we generate defect masks from the clean road image, and these prompts guide the system in simulating various road conditions. Next, we use these masks with the original clean road image to create the final image with defect. Let me explain how we developed the training data set for the road defect generator. As a reminder, this module is designed to generate defective road images using clean road images and corresponding defect mask images. Given the inherent difficulty in sourcing pairs of identical scenes with and without road defects, we decided to generate such pairs by inpainting road defect with clean asphalt. The process begins by creating clean road images from those with defects using their annotations. The original defective images are retained and used as the ground truth for training the road defect generator model. You can see our results here. For each column, the top area shows the original road with defect, serving as the ground truth for our model. And the image in the middle shows the corresponding defect mask, identifying the locations and types of road defects. The third row is the resultant defect-free clean road image, demonstrating the outcomes of our in-painting process. Audio modules in the pipeline are also implemented. If you are interested to see our examples, feel free to visit our booth. The next case study focuses on a project for a customer who needed synthetic number plate datasets specifically designed to withstand extreme lighting conditions such as low light and saturated light. Our first step involved generating images of cars with arbitrary number plates and generating images of number plates using specific prompts. Then we annotated the number plate areas on the generated car images. Incorporating Blender, we utilized the generated car images as background. After extracting the annotated rectangular areas for the number plate, we created separate planes, applied metallic shaders for authentic texture, and assigned various number plate textures on it. Modifying the lighting conditions within Blender enables the accurate simulation of challenging real-world lighting scenarios. Assessing the advantages, we obtained ground truth number plate strings directly from the prompts, ensuring data accuracy and reliability. The ability to simulate challenging lighting scenarios emerged as a significant advantage, aiding in the development of resilient recognition systems. Furthermore, the simplicity of requiring only rectangular annotations for the plates optimized the process, enhancing efficiency. So far, I've introduced our project, which we effectively met the customer's specific requirements using custom synthetic data set. Now, let me move on to the next topic, data curation. In the realm of deep learning, we often talk about a concept called the latent space. This is an abstract, multidimensional space that encodes a meaningful internal representation of externally observed events. The latent space plays an important role in deep learning, especially in terms of data compression. It allows us to learn data features and find simpler representations of data for analysis. For example, now let's look at how AIMMO uses data curation in the latent space to improve the quality of the dataset. Our goal is to identify a smaller dataset that can achieve performance comparable to the model trained on the bigger original dataset, while also covering edge cases. To do this, we first project each data sample to a point in the latent space. From here, there are numerous ways to refine a dataset in the latent space. For instance, we can find representative samples using clustering, or identify edge case samples through similarity measurement. And by offering tailored synthetic data solutions, AIMMO can generate more data samples around the identified edge case samples. In this way, we ensure our clients receive data that's optimized for their specific use case. While we've explored the potential and applications of generative models in synthetic data generation, it's equally important to recognize the challenges and limitations that come with it. One of the primary challenges is the significant computational resources and time required for training generative models. Moreover, the quality of synthetic data is intrinsically linked to the quality of the real data used for training. And while synthetic data can diversify data sets by providing various scenarios, capturing the entirety of real-world complexity in synthetic data remains a formidable challenge. The next two things are somehow connected. There are instances where generative models may produce unrealistic data, and to prevent this, we must find a way to evaluate the quality of the synthetic data. Last, the lack of interpretability and transparency in generative models can pose challenges in certain applications. In conclusion, generative models play a significant role in data-centric AI, especially in the field of autonomous driving. Using these models to generate synthetic data can greatly reduce the need for a lot of labeled data, making the development process more straightforward. AIMMO's specialized approach, focusing on operational design domains, effectively handles edge case scenarios, ensuring robustness and reliability. Additionally, improving the quality of data through careful curation in the latent space increases the effectiveness of AI models. While we recognize the challenges and limitations of using generative models, the substantial benefits they offer for synthetic data generation have been clearly demonstrated through our case studies. As we look to the future, it's clear that advancements in data-centric AI and generative models will continue to have a major impact on the development of autonomous driving technology. If you want to know more about our synthetic data and our data labeling service, we cordially invite you to our booth. Thank you for your attention.
Thank you very much. Very interesting presentation, and right on the time. We have time for one or two questions. Any questions from the audience? Any comments from the audience? Are you leaving, or are you going to ask a question?
I can ask a question.
Good. Maybe one for me is a little bit, I think you touched on it, but I mean, there's a bit of controversy as well. I'm sorry.
Yes, thank you.
You go first, please.
Thank you. So interesting topic. So we at AVI are also looking into similar directions for synthetic data generation. And one of the main challenge that we are facing, or when you do this kind of technologies applied, is temporal consistency, which means from one image to another. So could you comment how you tackle this challenge?
Yes, yeah, a lot of people have asked the same question to me. And actually, for now, the limitation of generative models like Stable Diffusion, yeah, prevents us to generate temporally consistent data. For now, I think it's better to use this kind of technology to generate the data that are not required to be temporally consistent. But I'm hopeful in this direction because day by day there are new Stable Diffusion papers in the internet, and there are a lot of researchers doing investigating into the direction of temporal consistency. So I'm optimistic that we can use this technology for the temporally consistent data.
Thank you.
Additional questions from the audience? Maybe one quick bonus question. Any plans to bring this into the 3D domain?
Yes.
Or you still have your hands full with 2D already?
Yes, I actually conducted a research at Bosch for generating 3D models with diffusion models and sign distance function.
Okay.
And yeah, at that time, I only did a pilot project, but it was promising.
Okay. But then we know the presentation title for the next time.
Okay.
Thank you for your presentation. Thanks for being with us today. Oh, sorry. Do we have one more from the room?
Yeah. So
okay, please.
And a short question. If I understand correctly, you use the generative AI model to then train this synthetic data, right? So that's a major difference. My question actually, what is the major difference in the results? Do we have the results when you use the older, let's say, AI model instead of generative model and to apply for the synthetic data? And now you use the generative model. What's the difference in the results? It's a major improvement. I don't see it, So.
Well, actually, what I presented in this talk was to utilize generative models such as Stable Diffusion to generate synthetic data. And the performance boost comes from this synthetic data is introduced in the papers that I presented. So I refer.
Do you measure this also on the real results?
Sorry?
Do you measure that also on the results of the performance? So at the end of the day, so you can, so using generative model to generate the synthetic data. But then, so you have then also, based on that, generate the scenario, right? And then you use that also in the real world to check, so how the performance it is. And that's one way, the older way, so not generative model, the older way. Do you have a comparison between these two?
I'm not sure I understood your question correctly, but the performance boost using this synthetic data on real data set as a test set is presented in the paper.
My question is, you generate the synthetic data
Yes.
in different AI models. And then that's where we also used, for the real data. So you need to train the algorithm and so on. I just want to know if you use these two different AI models,
Gentlemen, we have a little bit of an issue here because we have the next presenter waiting online. So may I ask you to maybe take this offline over the dinner? I think most of us will be at the dinner. I think it's a fantastic dinner conversation. And I'm getting signals from the back, so I'm sorry. Would you mind also taking it offline? Thank you.
I will heading to your table after.
You already have your dinner conversation topic set then.
Okay. Thank you so much.
Thank you. Thank you very much for your presentation.